In a laboratory just outside Nanjing, engineers recently poured a batch of concrete that contains, by deliberate design, 0% ordinary cement. This isn't some delicate experimental mixture that crumbles under the slightest pressure. It's structural grade, fully load-bearing material, the kind you could pour into a bridge deck. And it slashes the carbon footprint of the material by up to 90% compared to the concrete holding up virtually every building you've ever set foot in. If that sounds too good to be true, it's because cement has quietly been the construction industry's biggest climate offender for more than 100 years, hiding in plain sight behind every road, dam, and skyscraper on Earth. So completely taken for granted that almost nobody outside the industry ever stops to consider where it actually comes from. China just figured out how to build without it. Here's how they pulled it off. Before getting into the fix, it helps to understand exactly how broken the underlying problem really is. Cement, specifically Portland cement, the gray powder mixed with water, sand, and gravel to produce concrete, is responsible for somewhere around 8% of all global carbon dioxide emissions. To put that figure into perspective, if the cement industry were treated as its own country, it would rank as the third largest emitter on the planet, trailing only China and the United States as entire nations. A single industrial material, sitting quietly behind nearly every road, bridge, dam, and skyscraper humanity has ever constructed, manages to outpollute entire continents. The reason cement causes so much environmental damage comes down to basic chemistry, and it's a genuinely nasty combination of two separate problems. To produce Portland cement, manufacturers heat limestone inside massive rotary kilns to temperatures above 1,400 degrees Celsius, and that heating process alone burns through enormous amounts of fossil fuel. But here's the part that makes the problem structurally unavoidable using traditional methods. Heating limestone to that temperature triggers a chemical reaction called calcination, which releases carbon dioxide that's been trapped inside the rock for millions of years, completely separate from whatever fuel was used to heat the kiln in the first place. That means even if you ran the entire kiln on pure solar power with zero fossil fuels involved, you'd still be releasing massive volumes of carbon dioxide purely from the chemistry of converting rock into cement powder. The carbon isn't coming from the fuel. It's baked directly into the reaction itself, and no amount of clean electricity or efficient kiln engineering can fully solve that. China happens to produce more cement than the rest of the entire world combined, which means it also carries the single largest carbon liability tied to this material anywhere on the planet. And rather than simply accepting that as an unavoidable cost of building infrastructure at national scale, the way most governments quietly do, Chinese researchers and engineering firms spent the past several years pursuing a genuinely radical question. What if cement simply wasn't part of the equation at all? It's worth sitting with the sheer scale involved here for a moment, because it's easy to glance past a statistic like 8% of global emissions without truly absorbing what it means. According to figures widely cited among engineers and economists, China pours more concrete in roughly a 2-year period than the United States poured across the entire 20th century. Every ton of traditional cement carries its own built-in carbon debt embedded in the chemistry itself, which means a country building highways, high-speed rail lines, and entire new cities at the pace China does isn't just facing a large emissions figure. It's facing one that compounds and grows larger with every year construction continues at this pace. Fixing the material itself, rather than simply trying to build less of it, was always going to be the only strategy with a realistic chance of making a real dent in the numbers. The answer to that radical question turned out to be a material called geopolymer concrete, and the underlying concept has actually existed in academic circles since the 1970s, largely sitting unused because it never made economic sense to produce at industrial scale, until now. China is the country actually making it work in the real world. Instead of relying on Portland cement, geopolymer concrete uses industrial waste byproducts as its binding agent, primarily fly ash, the fine powdery residue left over from burning coal at power plants, and ground granulated blast furnace slag, a byproduct pulled directly from steel manufacturing. Both materials are aluminosilicates, meaning they're naturally rich in silicon and aluminum. When activated with an alkaline solution, typically a blend of sodium hydroxide and sodium silicate, they undergo a chemical process called geopolymerization, forming a rigid three-dimensional molecular structure that binds sand and gravel together into concrete every bit as strong as the traditional version, without a single gram of Portland cement anywhere in the mix. No kiln, no limestone, no calcination reaction releasing ancient carbon back into the atmosphere. The environmental math here is almost embarrassingly favorable once you break it down. Fly ash and slag are already being produced regardless, as unavoidable waste byproducts of coal power generation and steel manufacturing, materials that would otherwise end up in landfills or piled into enormous ash ponds. Geopolymer concrete essentially takes waste from one heavily polluting industry and repurposes it as the core ingredient for a dramatically cleaner version of another. There's no need to mine new limestone. No kiln needs firing to 1,400 degrees, and genuine industrial waste gets diverted away from landfills in the process. Depending on the exact mix design and which activator chemistry is used, life cycle studies from Chinese research institutions have measured carbon reductions ranging anywhere from 60% up toward 90% compared to conventional Portland cement concrete. The kind of figure that usually only shows up in a press release, except here it's actually being poured into functioning infrastructure. There's also a naming issue worth pausing on, because calling this material concrete honestly undersells just how different the underlying chemistry is. Traditional cement hardens through a process called hydration, where water reacts with calcium compounds and gradually crystallizes into a hardened matrix over the course of weeks. Geopolymer binder hardens through an entirely different mechanism, dissolving the silicon and aluminum atoms out of the fly ash and slag particles and allowing them to reassemble into a new glass-like molecular network structurally closer to natural volcanic rock than to hydrated cement. It's not a modification of the old recipe. It's a completely different chemical pathway arriving at a similarly strong, similarly performing end product, which honestly makes it more impressive once you understand what's actually happening at the molecular level. This is where the story stops being a laboratory curiosity and starts becoming a genuine industry, because nobody gets to claim they've solved a global emissions problem until they can produce the fix at a scale that actually matters. Several provinces across China have been building dedicated geopolymer production facilities, industrial plants specifically engineered to source fly, ash, and slag directly from nearby coal power stations and steel mills, blend them with activator chemicals under tightly controlled conditions, and ship out a finished binder product that ready-mix concrete plants can use as a direct replacement for traditional cement. Some of these facilities are physically located right next to the power plants and steel mills supplying their raw material, which cuts transportation emissions even further, since the fly ash and slag never have to travel far from where they were originally generated as waste. The real engineering challenge here wasn't the chemistry itself. Researchers have understood the basic geopolymerization reaction for decades. The challenge was consistency. Fly ash composition varies substantially depending on which coal seam it originated from and how the power plant burned it, and slag composition shifts depending on the specific steelmaking process used. That variability made it genuinely difficult to guarantee consistent strength and curing behavior from one batch to the next, which is a non-negotiable requirement if this material is going into a load-bearing bridge support. Chinese engineering teams developed standardized testing and blending protocols specifically to eliminate that inconsistency, essentially applying the kind of quality control rigor a pharmaceutical company uses on its raw ingredients to what is, fundamentally, industrial waste. Getting garbage to behave consistently turned out to be harder than getting fresh limestone to behave consistently, but they solved it anyway. There's also a certain elegance to the supply chain here worth pointing out, because it doesn't require building an entirely new mining operation the way traditional cement production does. Every coal power plant already produces fly ash as an unavoidable byproduct, and every steel mill already produces slag. That means the raw material supply for this new binder already exists, sitting in stockpiles across the country right now, some of it in ash ponds that have been quietly accumulating for decades and creating their own separate environmental concerns, including potential groundwater contamination. Turning that liability into feedstock for a construction material doesn't just cut emissions tied to new cement production, it actively shrinks a completely separate waste problem that previously had nowhere useful to go. Just when it seems like the story ends with eliminating emissions, some Chinese research teams push things a genuinely bold step further, developing concrete that actively absorbs carbon dioxide during the curing process itself, rather than simply avoiding emissions up front. This technology, sometimes referred to as carbon-cured concrete, works by injecting captured carbon dioxide gas directly into the concrete mixture while it's still curing. That gas reacts chemically with calcium compounds in the mix, forming solid calcium carbonate and effectively mineralizing the carbon dioxide permanently into the concrete structure. That reaction doesn't just neutralize emissions, It actually improves the concrete's compressive strength and density in the process, meaning engineers can sometimes use less binder material overall to hit the same structural performance targets, compounding the carbon savings even further. Pilot facilities across China have been sourcing captured carbon dioxide directly from nearby industrial flue gas streams, the same smokestacks that would otherwise simply vent that carbon straight into the atmosphere, and piping it into curing chambers where concrete blocks and precast panels sit and literally absorb it. Every block produced this way becomes a small, permanent carbon sink, locked into the material for as long as the structure stands, which for most concrete infrastructure means decades, if not centuries. Combine this curing technique with a geopolymer binder that already skips the emissions tied to traditional cement production, and the resulting concrete ends up fighting climate change from two entirely different directions before it's even been poured into anything. The scale potential here is genuinely enormous once you work through the math, because concrete curing happens continuously at industrial volume across thousands of precast facilities. Even a modest amount of carbon dioxide absorbed per cubic meter of concrete adds up quickly in a country pouring concrete at China's pace. Researchers have pointed out that if carbon curing were adopted broadly across the industry, the cumulative mineralized carbon dioxide could potentially rival the output of dedicated direct air capture facilities. Except this version doesn't require building any new capture infrastructure from scratch. It's essentially carbon capture arriving as a free side effect of a manufacturing step the industry was already performing, just with captured flue gas swapped in for ordinary air. Here's the thing that usually kills promising green building materials before they ever leave the lab. Being environmentally friendly doesn't matter much if the material can't actually hold up a building. So alongside all the emissions-focused work, Chinese researchers have also been racing to ensure these zero cement formulations aren't just cleaner, but genuinely stronger than what they're replacing. One of the more attention-grabbing developments involves reinforcing concrete mixtures with tiny quantities of graphene, the famously ultra-strong, ultra-thin carbon material that's been hyped across dozens of industries for over a decade. When graphene oxide gets blended into a geopolymer or cement mix at extremely low concentrations, sometimes under 0.5% by weight, it can dramatically boost the material's compressive strength, its resistance to cracking, and its overall durability against water infiltration. One of the primary ways concrete infrastructure degrades and eventually fails. In practice, Chinese manufacturers have been scaling up graphene production specifically to drive the cost down low enough to make this kind of reinforcement commercially viable in construction, a price point that would have sounded like science fiction just a decade ago, back when graphene cost more per gram than gold and was mostly confined to electronics labs rather than anywhere near a concrete mixer. Combining graphene reinforcement with a geopolymer binder gives engineers a material that's simultaneously lower carbon and higher performance, a genuinely rare pairing in materials science, where improving one property usually means sacrificing another. Normally, going greener means giving something up. Here, apparently, engineers get to have both, which almost never happens, and honestly feels a little too good to be true until you look at the actual test data. There's a durability angle here that matters just as much as raw strength, even though it gets far less attention. Concrete infrastructure rarely fails because it can no longer support enough weight. It fails because water and chloride ions slowly work their way in through microscopic cracks over the years, corroding the steel reinforcement bars buried inside and eventually causing the whole structure to crumble from the inside out. Graphene's molecular structure happens to be exceptionally good at blocking exactly that kind of moisture infiltration, forming an almost impermeable barrier at the microscopic level, even at tiny concentrations. Chinese researchers testing graphene-enhanced geopolymer samples have reported meaningfully extended service life projections compared to standard concrete, which matters enormously for infrastructure meant to last 50, 75, or even 100 years without a full rebuild. Cement isn't the only ingredient in concrete facing a supply and sustainability problem, though. Concrete also requires sand and gravel, collectively known as aggregate, and the world is burning through usable construction sand at a genuinely alarming rate. Desert sand, oddly enough, is too smooth and rounded from wind erosion to bind properly in concrete, which means construction relies almost entirely on angular river and quarry sand, a resource being depleted so quickly in some regions that illegal sand mining has become a serious organized crime problem in parts of the world. China has been tackling this from two directions at once. On one side, as part of a broader push toward construction waste recycling, crushed demolition debris is being processed into recycled aggregate that can substitute for a meaningful share of the virgin gravel and sand a concrete mix would otherwise require. On the other side, researchers have developed specialized treatment processes that make ocean sand and desalinated sea sand usable in concrete mixes, something traditional formulations historically struggled with, since residual salt content corrodes steel reinforcement bars from the inside out over time. New geopolymer formulations, it turns out, tolerate sea sand and its salt content considerably better than traditional Portland cement mixes do, partly because the alkaline activation chemistry behaves differently around chloride ions. That opens up an enormous new aggregate supply along China's own coastline, one previously considered off-limits for serious structural work. Put those two pieces together: waste-derived binder replacing cement, and recycled or ocean-sourced aggregate replacing virgin sand and gravel, and you get a concrete formulation where almost none of the core ingredients had to be freshly mined or quarried out of the ground at all. It's concrete built almost entirely from other industries' leftovers. It's worth pausing on just how strange the global sand shortage actually is once you say it out loud, because most people assume sand is essentially infinite. There's a literal desert full of it, after all. But desert sand grains get tumbled and rounded smooth by decades of wind erosion, meaning they don't interlock the way angular river or crushed rock sand does. A pile of desert sand the size of a mountain is, functionally, almost useless for structural concrete. That's the quiet irony that sat beneath global construction for decades. Some of the sandiest places on the planet still have to import usable sand from somewhere else. Unlocking treated sea sand as a viable substitute doesn't just address an emissions problem. It solves a genuine physical resource scarcity that most people walking past a construction site have probably never even considered exists. None of this matters if it stays confined to a research paper, and this is really the part that separates China's approach from a lot of promising green building materials that get announced with great fanfare and then quietly disappear because nobody ever scales them past a demonstration project. Geopolymer concrete has already been poured into real infrastructure across multiple provinces, including road pavement projects, precast wall panels for residential and industrial construction, and sections of bridge infrastructure, where engineers have run extensive load testing to confirm the material meets the exact same structural codes as traditional reinforced concrete. Some high-speed rail construction projects have also incorporated geopolymer-based precast elements, specifically because precast factory production allows for the kind of tightly controlled curing conditions that help resolve the batch-to-batch consistency challenges mentioned earlier, since the material isn't being poured on an open job site at the mercy of weather and temperature swings. Engineers overseeing these pilot segments have reportedly run the material through the exact same fatigue and load cycling tests applied to conventional concrete rail infrastructure, essentially declining to give the new material any special treatment or lowered standards simply because it's greener. That's probably the single biggest reason regulators have felt comfortable approving it for genuinely load-bearing public infrastructure rather than restricting it to decorative or non-structural uses. The economics are ultimately what will determine how quickly this scales nationwide, and right now the picture looks genuinely favorable. Fly ash and slag are, again, waste products that industrial facilities often have to pay to dispose of anyway. That means geopolymer binder can, in many regional markets, actually come in cheaper than traditional Portland cement once local supply chains are established near the power plants and steel mills generating the raw material, rather than more expensive, which is how most green alternatives tend to behave when they first hit the market. Cheaper and cleaner is an unusually easy sell to a construction industry that runs on razor-thin margins and has little patience for materials that only make financial sense on a spreadsheet built around future carbon credits. There have also been early trials integrating geopolymer mixes into low-rise residential and industrial building projects, not just large infrastructure, testing how the material performs in more conventional construction settings, where builders are accustomed to the predictable working time and finishing behavior of ordinary cement. Geopolymer concrete does behave somewhat differently on the job site. Curing characteristics and workable time windows can shift depending on the exact activator chemistry and ambient temperature, meaning contractors have needed some retraining and adjusted procedures rather than treating it as a pure drop-in swap on every job. That's less a knock against the material and more an honest acknowledgement that changing the fundamental chemistry of the world's most heavily used building product doesn't happen without some kind of learning curve, even when the finished product performs exactly as intended. Step back now and look at what's actually unfolding here. An industry responsible for roughly 8% of all global emissions, hiding in plain sight inside every road and building on the planet, is quietly being rebuilt from the chemistry up. Fly ash and blast furnace slag, byproducts that used to simply pile up in ash ponds and slag heaps, are becoming the primary ingredient in a new generation of structural concrete. Captured carbon dioxide that would have vented straight into the atmosphere is instead getting mineralized permanently into curing concrete blocks. Graphene, once a laboratory curiosity too expensive to use in anything practical, is quietly making that same low-carbon concrete stronger than what it's replacing. And even sand, one of the most overlooked resource crises in modern construction, is now being sourced from recycled demolition rubble and treated ocean sand instead of vanishing riverbeds. None of these pieces exist in isolation, and that's really the pattern worth noticing at this point. China isn't chasing a single silver bullet green cement additive to bolt onto the existing system and call it finished. It's rebuilding the entire supply chain behind concrete simultaneously, from the binder to the aggregate to the curing process itself, treating an industry most people never think twice about as one of the biggest and most solvable climate problems sitting in plain sight. That's really the story underneath all these numbers. Concrete is, by volume, the single most consumed material on Earth after water, which means even modest percentage improvements here dwarf almost anything happening in flashier, higher-profile industries. While other countries are still funding pilot projects and drafting white papers about the theoretical potential of geopolymer chemistry, China is already pouring it into bridges, rail lines, and apartment blocks that people are living in right now. Consider how strange all of this would have sounded to a construction engineer just 15 years ago. Concrete without cement. Concrete that gets stronger by absorbing carbon dioxide instead of releasing it. Concrete reinforced with a material once too expensive to produce in anything beyond microscopic laboratory samples. Concrete made from beach sand instead of riverbed sand, poured next to a coal plant, and using that same plant's leftover ash as the glue holding it together. None of these individual ideas are entirely new. Researchers have floated versions of each one for decades across academic papers and small pilot studies scattered around the world. But stitching all of them together into a functioning, cost-competitive, code-compliant industrial system is the part almost nobody else on Earth has managed to pull off at national scale. The foundation of the built world is quite literally being rewritten, one waste-derived, carbon-absorbing, graphene-reinforced batch at a time. And most of the world hasn't even noticed the ground shifting beneath it yet. Zoom out even further, and the significance of this shift becomes harder to ignore. Cement has been a fixture of human construction for roughly 2,000 years, tracing back to early Roman concrete, and it became the default building material of the modern industrial era precisely because it was cheap, reliable, and available everywhere limestone could be quarried and burned. Nobody engineered it to be a climate liability. It simply became one as global construction scaled up to a size nobody in the 19th century could have imagined, turning a locally useful building material into a planet-spanning emissions source almost by accident. What China's geopolymer push represents isn't a minor tweak to that 2,000-year-old formula. It's closer to a full replacement of the underlying chemistry, developed not in a Silicon Valley startup or a European research consortium, but inside state-backed engineering programs willing to run the material through actual bridges and rail lines rather than leaving it confined to conference posters and laboratory press releases. That willingness to deploy at scale, rather than endlessly pilot and refine, is arguably the single biggest differentiator in this entire story. Plenty of countries have geopolymer research programs. Very few have geopolymer bridges people drive across every day. There are, of course, limits worth acknowledging honestly. Fly ash and slag supplies aren't infinite. They're tied directly to how much coal power and steel production a country runs, which means as China's energy mix eventually shifts further away from coal, the raw material feedstock for this exact formulation will need to evolve alongside it, likely toward other industrial byproducts or entirely different activator chemistries. Sea sand treatment adds cost and complexity that virgin river sand never required, and contractors accustomed to the predictable behavior of ordinary Portland cement still need retraining before geopolymer becomes a truly universal, no questions asked substitute, rather than a specialized option reserved for pilot projects and demonstration sites. But those are refinement problems, not fundamental ones. And refinement problems tend to get solved once an industry has real financial incentive and political backing pushing it forward, both of which are clearly present here. China has already shown the core chemistry works at structural scale, that the economics can undercut traditional cement rather than trail behind it, and that regulators are willing to hold the material to the same rigorous safety standards as anything else holding up a bridge or a rail line. So the next time someone drives across a bridge, walks into an apartment building, or rides a high-speed train somewhere in China, there's a real chance the concrete underneath them contains not a single gram of traditional cement, built instead from a coal plant's leftover ash, a steel mill's discarded slag, captured carbon dioxide pulled from a smokestack, a whisper of graphene, and sand pulled straight from the ocean. An industry that hadn't fundamentally changed its core chemistry in 2 centuries is being quietly rewritten in real time, one waste-derived, carbon-absorbing batch at a time. And the rest of the world is still largely watching from the sidelines, treating as theoretical what China has already turned into infrastructure.